Okay, let's get going. So today we are going to talk about, this is kind of the big topic of the day, is hashing, which is completely different than anything else we've really talked about so far in the class. So it also happens to be an extremely important part of computer science programming in general, is this idea of hashing, and we'll find out why. Here's the actual schedule about what we're going to do today. Unix tip of the day today is going to be on regular expressions. So on Monday, I mentioned that some things like sed and grep actually use regular expressions in their when you're doing searches for things. And I'll actually dig a little bit. I figured I might as well dig a little bit deeper into that and kind of show you what a regular expression actually can do. And then when you see it again in some future class, or when you're doing some JavaScript or Perl programming or Python programming or something like that, you'll say, oh, regular expressions, I've seen this before. I get it. OK, I also have a couple comments on homework 4, which is ongoing, as you know. And then I'll open up for questions, too, if you have any. And then we'll talk about homework 3 and the grades. If you should have already gotten an email back with your homework 3 grade. If you didn't, one of two things could have happened. Either it didn't get into provide correctly, which actually has happened to at least one or two people. I'm not exactly sure why. I still have to figure out why. Or the email system that we use to email grades didn't work. So if you didn't get a grade on that, let me know, and I'll send it along or figure out what the story is. And then we will talk about hashing. Any questions before I begin? OK. All right, so the Unix tip of the day. So I mentioned regular expressions the other day. Regular expressions are simply sequences of characters that allow you to that form some search pattern in that you're going to use to search through some text. OK, sounds pretty basic. It turns out regular expressions are like super duper powerful. OK, here's how I'm going to give you a couple examples here. So the most basic regular expression is just a simple character. OK, and depending on which regular expression engine you're using, it may only match the first character, or it may match all of them. I'm going to show you the one where it matches everything. So for instance, in this case, A actually matched. If you have the regular expression A, and you were looking at the string and the apple was eaten, it would pick out this A, and that A, because that's all the A's in there. Fairly straightforward stuff. OK? If you want to match multiple characters or multiple letters, you'd put the series in a little bracket. And that would say match either A, E, or A. OK? And you can put anything in there, 1, 5, 7, whatever your match is. Then it will say E and A and E and A and E and A and E, and whatever. Finds them all in brackets. OK? You can also match ranges, which is kind of cool. A lot of times you use regular expressions to match whether or not a string is just digits or not. You would put 0 through 9 in a little dash like that. And then if it matches, then you say, oh, it's just digits. Or you could say there's actually a not character as well, which would say don't match the characters, like the letters. So but if we did A through M here in brackets, that says match any of the characters A through M, meaning it would pick out T, H, E, A, L, E, A, etc. Anything between A and M. Online, you can test these. There's lots of regular expression testers online. So if I did EA, sorry if the font, I'll make this a little bit bigger. There we go. All right. So if I want to match EA in brackets like that, and I said the apple was eaten, it actually shows you what gets matched. It actually color codes it like as well. OK, so that's kind of cool. And you can go to the website here, regexpal.com, and you can do that. OK. Let's look at another example. There's also some wildcard rules. A period in a regular expression means match any character. So A period period would match A and then period, then period. This is not in brackets, so it has to match all three. So it would be A, P, P, and then A and S, and then the space, which isn't red, and then A, T, E. OK, see how that works? Star is another wildcard variable, but possibly different than you may have used it before, like if you're looking through directories. What it is in this case is it matches 0 or more repeats of the previous character. So P star would match any number of P's. Okay? And this is where it starts to get really important and really powerful. When you can have all these wildcards that match certain groups of letters, it's pretty cool that way when you do it. If you end up taking a compilers class too, you may end up talking about regular expressions and how how you actually parse through code in a compiler, like in a compiler, when it looks at your code and says what word is this, et cetera, et cetera. It uses regular expressions very frequently. If you do a period star, that would mean a followed by any character repeated 0 or more times. Well, that matches anything past the first a, basically. It says a and then any character, and then any character repeated, meaning it can be any of the other characters. You can also anchor strings, which means if you want one at the beginning or the end, you have these like caret, which means at match the beginning, or the little $, which means that match the end. Okay, so if you put caret THE, it would match the whole thing, because it would be just this one all the way to, well, actually, no, sorry, it would just be the THE. I don't know why that's red. But in this case, it would do that. If you match caret apple, it would not match any, because apple's not right at the beginning. Fair enough? And then D period $, says match anything that is D and then anything else at the end. In this case, it happens to match D period, but of course, the period is a wildcard, so it would match anything where D, anything at the end. You have to be a little careful with these two, because it's a wildcard. So, for instance, if you wanted to include a special character, like the period itself, you have to put a backslash there. That's called escaping it. Don't worry about the details of that, but it's called escaping it, meaning if I want to match exactly poisoned with a period, I'd better put a slash there so it says not a wildcard anymore, just a period. And then this one, poisoned / period, would not match here because there's no period after the poisoned. Cool? And then this one was pure poisoned periods. Same, this one would match because that's now a wildcard. So you have to be a little careful with this. As I said, lots of places you can look these things up. grep and sed use them for their matches. Other editors use them. I think Emacs especially uses regular expressions very frequently. Questions on it? No. Did you guys do any regular expressions in Comp 50? No? OK. You might. It's one of those things I could have seen you do it, but I guess you didn't. OK. No other questions on that? Awesome. All right. Homework 3. As I said, you should have gotten your grades. If you haven't, email me. The grades were pretty good for homework 3. All things considered, the grades were pretty good. If you did do poorly on it or want to know what the story was with your grade, email me as well, and I can we can talk it over. But for the most part, very good. I know it was a hard assignment, and I know it was also kind of an assignment that had some tricky logic in there, and I know you guys worked hard on it. So good job overall. Homework 4. We have had lots of good questions on Piazza. Okay, lots of good questions the kind of questions I was hoping would go on Piazza for this assignment, like, hey, if I choose this kind of gap sequence or this kind of gap sequence, how do I make that decision for shell sort? That's, that kind of question is kind of a cool question, and it's a lot more fun than, do I use a semicolon here, or is it a bracket, or that sort of thing. So I'm glad that's going well for some people as far as asking those kind of questions. I was talking about this a little earlier before most of you guys came in. The whole point of this assignment was to kind of broaden the spectrum for your own desire to work hard on this project. If you want to kind of make it a standard project that's really not that hard, you can do that. If you want to go above and beyond, absolutely you can. Okay, and there's no grade differentials between that either. I mean, you do the standard project, you pick 3 relatively straightforward sorts, and you do them. That's fantastic. But you can also go above and beyond. So I'm glad that's happening. A lot of the design choices are definitely up to you. Make sure you comment them in your README file and in the actual code. So if you end up using a stack or something for some sort, which would be an odd choice, I'd say, in general, then you should probably justify it and justify why you did that. The README TXT file is going to be really, really important, because in there you have to, number one, explain your algorithm that you used. Okay, I mean, it's going to be more or less the same for all the merge sort or all the selection sort ones, right? But if you used quicksort and you did something interesting with it, like I know some of you have, then explain that and talk about why, again, why you made the choices you did and how it affected the actual running time of your sort. You do not need to talk about, or you do not need to go ahead and try to derive average complexity. Okay, that's way beyond the scope of this class in terms of deriving it. You can look it up for certain sorts. You can give it your best shot. You can say, you know what, I came up with this sort. Here's what I think it is. Here's why. But I do not expect formal proofs of why the average complexity is the way it is. It's just, remember, some sorts, like shell sort, don't even have defined average complexities because nobody's figured them out yet. Or they're unfigure-outable, right? So, but in the end, you do have to talk about the complexity. You should be able to figure out the worst case and best case based on your either your own testing or analysis. But the average case, you should talk about if you can find a reference or give it the best shot. But I don't expect you to know how to do that. OK? Any questions on homework 4 at this point? It's going all right, I hope? I think it sounds to me like people who started it said it was cranking along OK. But oh, there was some other concern about having TAs in lab last night. I don't think there actually were any. And the schedule is kind of ambiguous as to whether there should have been. So we'll try to get more lab TAs kind of fleeting up as the next couple days go along, because I know it's due Sunday. OK? Any questions on that one? Comments on homework 4? Lingering concerns? No? OK. All right. So now we're going to get on to our next topic, which, as I said, is hashing. And I just wanted to set it up for you for a sec. And we're going to kind of come back to this little example in a few minutes. But let's say you have some 2-letter words. And that's the only amount, like you're only dealing with 2-letter words, right? It's like kindergarten level 2-letter words. OK? For instance, ox, right? And we want to store we want to be able to like match those 2-letter words with their definitions in some data structure. Okay? So in particular, we're going to have the keys, which we've talked about before, right? In this case, the keys are going to be those 2-letter words. And the values of those keys are going to be the definitions that we're trying to actually store. Okay? And the key here, no pun intended, is that we want to store them in an efficient data structure. Okay? Now, we've been talking about that the whole class, right? I mean, what's an efficient data structure, blah, blah, blah. And we've done pretty well with some of these data structures, right? We have already discussed a number of different ways that we could do this, right? You guys, if I said, here's some words in dictionary definitions, go put them into some data structure that you've already talked about, you could probably find a list structure like an array or a linked list to put them into, or stacks and queues is a little tough we'll get to that in a second. But trees, you could do that in there. And all they have to do is have 3 different functions. Okay? The functions we're going to need to do are find, right? In other words, find the definition based on the word. Insert, obviously, you have to get it into that data structure. And remove. All of these that we talked about have some compromises you have to make. Or in some cases, you can't even do these. Like, for instance, is it possible to do a find on a stack or a queue? Why not? You can't view all, like, the definition of a stack is you only get one value you can look at, right? Which one? The top. Yeah, you can look at the top of a stack, that's it. Now, sure, you could build something in and be like stack plus plus, right? Where it's like some extra part of stack where you can now look down and find it, but that's not really a stack anymore, right? Then it's just kind of an array or whatever other underlying structure you're using. So stacks and queues couldn't even really do that if you're going to keep with the definition of stacks and queues. But lists and arrays and linked lists, there's trade-offs. Right? When we talked about the priority queue, there were trade-offs on having doing the inserts versus in a sorted array or a not sorted array or whatever. And they all had some case or another that either had log n behavior or order n behavior. We want to do better than that. Okay? We want to be able to do these 3 things better than order n or better than log n behavior. Okay? That's kind of the overall goal. What do we do? Well, this completely different method that I'm talking about here. Okay? You can store keys and value pairs that actually enable you to get constant time insert, find, or search and remove. Okay? To a first approximation. We'll talk about the reasons it's tough to do that in the big spectrum as we go along. But you can do a system that will do that. Okay? We call that hashing. Okay? And I'll describe what hashing is in detail. But what the big thing about hashing is you have to use this thing called a hash function to make it actually work. Okay? And when you have a hash function, and by function I actually mean like literally a mathematical function that you're going to apply to your keys. It's going to run through that mathematical function and then spit out some value. Okay? So you're actually going to have to do that. Now, the question is, how do you do a mathematical function on the word ox? Have we done anything like that in the last few days? Like the lab? All right? We in the lab that we did tries, right? We walked through a string and looked at each individual character, and each individual character had an associated value with it, right? So you can do that. In the end, really anything that you throw into a computer, any objects or any strings or any other types of data, in the end, it's all numbers, right? I mean, really, when you get, this is part of that. This is the philosophical part somebody was wondering about, right? When you put things into a computer and it is storing them, it is storing that data as numbers, right? Regardless of how you process it, whether it's a word or an object or whatever, when you go deep enough, it's a number, right? So you can apply this, some sort of mathematical function to that data, okay? All right, when we do a hash function, what we get back is called the hash value, it's called the hash code, or sometimes we just call it a hash, okay? You apply a function on something, get back the hash on it. And that hash is going to be another number in some form or another. Questions on that? Okay, we'll get into more details in a little bit. Now, some of you may have noticed the numbers around here, right? Those are not from like some other class. This is like, I put them up earlier, right? Actually, I put them up this morning and then like crossed my fingers, they'd be up again, and they remained, so that was good. But here's what we're going to do. I'm actually going to hash you guys, okay? Which is going to mean getting up and like, you know, putting your laptop down and all that, so I apologize in advance. But here's what we're going to do. Okay, you all have a birthday, right? I do not care when your birthday is. If you want to lie to me about your birthday, that is perfectly fine. What I would ask is don't make your birthday a decade like away from when your birthday is, right? Like keep the decade when you were born roughly the same, okay, or the same. Okay, but otherwise, if you want to pick a day and you want to say I don't want anybody to know I was born on whatever, April Fool's Day or whatever, right? I don't know why you wouldn't, but some people get worried about that. Just make up a birthday, but don't change it during this whole exercise. Fair enough? Okay, here's what I want you to do. And even though we don't know much about hashing, what I'm going to do is we're going to apply a hash function, actually a number of hash functions, on your birthday. So the first one is going to be the decade of your birth year. So in other words, if you were born in the 60s, right, the 6 is what your hash number is, your hash is going to be. Make sense? Okay, here's what I want you to do. Get up and then go to the decade of your birth year, that one number in the decade of your birth year. Okay? Go ahead and do that. And just stand as close as you can. You don't have to go all the way in and whatever. They're kind of near the walls. It's getting a little crowded, isn't it? All right. Are you participating? Hey, there you go. Noah Mendelson is sitting in the back. He's also another professor of the practice here at Tufts, and I suppose he's participating as well. So a couple things about hashes. First of all, they need to be deterministic. In other words, if I sat you all back down again and said, go hash yourself by the decade of your birth, unless you change your birthday, aren't you all going to go back to the same place again? So is this hash, the decade of your birth year, deterministic? It is. Is it fast? In other words, and what I mean by fast is not how slow you guys are to like walk all the way down here, right? What I mean is it fast in, was it hard to calculate? All you need to do is divide by 10 and then do a modulus of 10. That's very fast for a computer to do, right? So it is fast and it is deterministic. Is it distributed? In other words, are you guys nicely distributed around the room, right? You are absolutely not, right? Because I think most of you were born in the 90s, right? Right? I would be, sadly, I would be over in the 7 over there, because I was born in the 70s. But most of you guys, in fact, probably all of you, anybody born in the 80s? Anybody? No, nobody. So you're all in one bucket. Okay, this is what's called a poor hash function. Okay, because you're not distributed at all. Okay, let's try another one. Let's go with the last digit of your birth year. Okay, so pick your birth year and go, what's the last digit, and go to that number. you born in?
1990.
Oh, nice. Well, you made it in the 90 pile anyway. There you go.
I would have blended it.
Right.
Big enough.
Right. All right. So we're getting there. It looks like, I suppose you guys are all at the 5s, and you guys are all at the 4s, and you guys are at the 3s up there? Yeah, this is kind of a tri-modal sort of hash right now, right? Because why? Because most of you guys are sophomores, juniors, or freshmen, sophomores, or juniors, right? So the odds are you're going to fit in that same category. Now, Noah back here happens to be also in the 3 category because I assume he was born in some year that ended in 3, right? So, so we won't go any more details. But anyway, the point is that this one did distribute it a little bit more. Was it deterministic? Yeah, as long as you didn't change your birthday, you're going to end up in the same ones before. Was it fast? All you had to do was mod by 10. That's pretty fast. Computers can do that fast. It's not the fastest computation around, but it's fast enough. And it was more distributed than before. Not perfect, because obviously, look, no one's over at the 9, 8. Sam's the lone person over here at the 0. A couple are at 1, right? So we've only got a few different kind of big groups. So it's not particularly distributed. Not the best hash code in the world. Try this one. The last digit of your birth month. So number the months from 1 to 12, and go to that digit. Okay, December being 1. I'm sorry, January being 1. That's what I'm talking about. Some people just stay where they are, right? Yeah.
92.
All right. Now we're getting a little more spread out, right? Was this hash function, the last digit of your birth month, was it deterministic? Yep. Was it fast? Same fast, really fast, right? Was it, is it distributed? More or less. What are the 2 buckets that probably have more people in them?
1 and 2.
1 and 2, why?
November,
November, December, and January and February, right? January is the same as November, and December is the same as February, right? So, yeah, so it's better. Can anyone think of an even better one? The day, yeah. So try this one. The last digit of your birthday, right? The actual day you were born on. So if you were born on the 7th of the month, it'd be the 7th. Now this looks much better. Right? So this one, again, 3 questions. Deterministic. Yes. Fast? Yes. Distributed. About as good as you can do, right? I don't know if there's not that many people over at 3s. You guys all over at 3s? But yeah, there's a couple numbers that aren't going to quite be distributed. Which ones? Well, I guess 1 really. Just 1, right? Because there's 31 days in some months and not in others, right? So yeah, this is about as good as you're going to get for birthdays, okay? And this is the kind of hash that you could use for if you had a system like you go to the DMV, and they might hash you based on the last day of your birthday because they have 10 different buckets they want to put in, right? You could do this, sometimes you go, I don't know if you've ever signed up for anything where they put you in lines based on the first initial or your last name. And all the ranges are different, right? Because there's nobody in not as many people in the YXZ kind of range, right? XYZ range. But there's a ton of people in the ABC or whatever. So they have to mix those up. If they did it by the last day of your birthday, it would be nice 10 easy buckets, right? So not too bad. Okay, have a seat. Good job. Yeah, this is the tricky part too, getting into your row without having to climb over too many people. This is like a double-ended stack or something. Yeah. Okay, so now you kind of have a basic idea of what hashing actually is. Okay, now you've seen it on your own birthdays. Let's get into a couple more details here. Here is a possible definition for a hash function. Any algorithm that maps data to a number that is deterministic, which you just saw, right? We mapped your birthdays in this case to numbers that are deterministic. Okay? And let's take an example of our actual like 2-letter string, okay, and see what we can get on this one. If we take ox, for instance, and we say that the letters are based on each letter has a number associated with it, and this is what we did with the tries in the lab, right? We subtracted the character A, and then we got the letter based on, or the number based on the letter's ASCII code, as it turns out. What we're going to do here is we're going to assign them all like this, and then for that 2-digit or 2-letter word, we're going to make up our hash as the following function. We're going to say that it's going to be just like you would do decimal numbers, right? Except we're going to use characters which happen to have 26 digits. If you're going to do 45, right? This is like 3rd grade kind of stuff, right? 45 is 10 to the 1 times 4 plus 10 to the 0 times 5. And 10 to the 0 is just 1. So this ends up being 40 plus 5, which is how you get 45, right? We're going to do the exact same thing with our 2-letter words, such that ox, for instance, would be 26 to the 1st power, right, times 14, because if you go along and you get to O, that happens to be 14, plus 1, which is 26 to the 0, times 23, which is where you go all the way over and you get to x. Add those two together, you get 387. Okay? I will let you ponder this for a sec, because there were a whole bunch of questions on that in the earlier class. Okay? You can also do the same thing with at. Okay. Just make sure you kind of get it. Yeah, Margaret.
How about the deterministic part? There's many ways to add up to get 387, but what keeps us from getting 387 any other way than powers?
Very good question. There are a number of ways to get to 387 by adding two things together, right? I will argue that there is only one way to get to 387 if you number it this way and you apply this function, 26 to the 1 plus times the number first number plus 26 to the 0 times the second. Just like I would argue that there's only one way to get to 45 in decimal, adding that together in decimal numbers, right? If you have 2 digits, how else do you get 45? There's no other way to get 45, right? It's exactly the same idea. We're just making 26 characters. This is really a base 26 calculation, right? Base 26 calculation, why not? And we're only doing lowercase letters in this case, or we're converting them. Yeah, Dylan.
Is there any reason why we've limited ourselves to 2 letters?
Is there any reason we would limit ourselves to 2 letters? Yes, and you'll see why in a second. Okay? But that's a very good question. Could we do the same thing on multiple letters? Sure. Or multiple size words? Sure, we would have to make some trade-offs, and we'll see what the thing is. But for now, just pretend our dictionary is like second grade or kindergarten dictionary, 2-letter words, that's it. OK, everybody see how you do at? You do 26 times 0, 26 to the first power times 0, because a is 0, plus 26 to the 1, 26 to the 0, which is 1, times 19, which is where t is. Right? Makes sense? OK, good. All right. So that's our population. That's our like first try at a definition for hashing, for a hash function, for this, right? Why does this help us get that order 1 access? Well, watch what we can do with that. If we have those distinct numbers, like 387 happens to be ox with our hash function, if we hash the word ox and get that 387, and then have an array, right? At the 387th point, we put the definition of ox, right? A bovine animal that's used for farming or whatever the definition is. I think I had it on the previous page, right? Then we can put it in that, we put the definition in that location. The next time we want to look up the word ox, apply the hash function. It comes out 387. We go to 387. As long as it's not empty, we pick that answer out, and that is the definition of ox. See how that's order 1 or constant? The hashing function does not depend on anything but it's supposedly a very, I mean, it should be a very fast function, Okay? And it's not based on like the number of words we've put in the dictionary. And looking up in an index in an array, we already know that's order 1. Okay? So do you see how we now have order 1 access for our function, right? For all of our words. Awesome. We have arrived. We can close the book. We can take our final. We can go home, right? We've got order 1, which is exactly what we've always wanted, right? Forget about all those other data structures. Always use hash tables. It's great. I wish it was that easy, right? Computing would be a different field if it was quite that easy. Anybody can anybody think of what one of the problems with this one might be? Yeah, Allie.
Well, like in this case,
Yeah.
if you needed, at least 387.
Yeah. In fact, how many do you need?
A lot more. 26.
26 squared, right? Which is like 600 and something, 670 something or whatever, right?
That's a lot of wasted space.
And in this case, it's a lot of wasted space. Yeah, it depends how many words we have. Now, the thing is, here's the great thing about this, though. Can't we store every combination of 2-letter words in this and get order 1 access? We can. So for 2-letter words, right, you can do this, and it works great. But you're absolutely right. There's a bit of a space issue here. And maybe there's a bit of a space issue here if we have some other like cases that we're going to talk about in like the next slide, probably, right? Probably. All right. So we can now insert, we can now find, and we can now delete. And delete is easy too. Hash the function, go to that location, and just either if it's a pointer or whatever, make it a null pointer, or just make it the empty string, or whatever your definition of not there is. Okay? And so all those operations are actually very fast. Okay? Back to this again. Okay? We're looking at all the 2-letter words, okay, keys and values, and we have 226, I guess it's not the next slide, 26 by 26, and we know how to hash it now. This is how many there are. Yep, 0 to 675. By the way, we call these buckets. I mentioned that kind of when we were going along. I said, you're all in one bucket or not. In this case, we call these things, these locations buckets, because you're kind of throwing them into a bunch of buckets, right? Here's what the program looks like to do this. Anybody recognize this language?
Oh yeah.
Oh yeah. That took way too long, Allie. You spent a whole semester with this language, right? Oh yeah. Allie, what language is this?
This is beginning student language. It's Dr. Rack.
It's Dr. Racket, or in other words, Scheme. It's Scheme, which is known as a Lisp-based language, which is what all the 50 students did in their last class. Now, I will not make the rest of you understand the beauty of this language right now. So I will do it in C++ for you as well. But I just wanted to throw that out for you guys, just so you could see it again, have like a little, memory, right? In this case, so here's what it looks like in C++. Okay, it's fairly straightforward. It is arguably not as beautiful as the Scheme, but it's all right. Here's what we have. OK, notice this. We're going to take the first character of the word minus a, which is what we did for the trilab, multiply it by the number of letters, which happens to be 26, and then add the second letter, which is exactly what we just said we were going to do. OK, that's our hash function. The word, OK, is going to be the actual word we're trying to hash. And what we can do over here is we go ahead and we have the def table, which is our array. And whenever we want to insert into it, we just set the hash code of the word in the right location. Done. Right? It's fast, and it's simple, and it's done. And finding is exactly the same. No looping, no order n, or no going to the next node or anything. None of that. Right? You just don't need to. There's an array there, and you have the hash code, which is the location, the index in the array, and you're done. Okay? So not so bad in the grand scheme of things. In fact, a pretty easy program to write. It was actually harder for me to write it in Scheme, but only because I don't really know it that well. But you could write this in any language, obviously, and do it that way. But that's how easy it is to do these hash tables. As long as you have a hash function or hash code, hash function, hash code, that and in here you can put whatever hash code. We'll talk about some more advanced hash codes in a few minutes. Okay. All right. Here's kind of what we were talking about earlier. What if you wanted to store longer words? Turns out there's a word that has 189,819 characters in it. Right? Now, this is actually a disputed word. In other words, it's a chemical symbol. Anybody in chemistry, you know how you can, there's like a formula for adding chemical names together, and you like add them together, blah, 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 right? Well, somebody in chemistry like came up with this thing, and it's this giant molecule, and when you write it all out, it's 189,000 and change characters long. So anyway, it's disputed. There are other words that are not as disputed. The longest published word, 1,900 characters. Longest word coined by a major author. Somebody wrote a 183-letter long word. I don't know why. Largest word in the major dictionary. Go up in the dictionary. You can probably find this word. I don't even know how. Pneumano ultra microscopic. I don't even know how to pronounce it. Right? Supercalifragilisticexpialidocious. Famous for being Mary Poppins. Okay, 34 letters. Okay, we have words that are or words that are not 2 letters long. Okay, so something may break down a little bit. Okay, there are also words. Anybody ever been to New Zealand? You been in New Zealand? So when I was living in Australia years ago, not last year, like most of you guys thought, when I was living in Australia, I actually took a trip to New Zealand, and in my Let's Go travel guide, they talked about this. The longest place name in the world is located in New Zealand, and here it is. It's Taumata, right? And I actually drove to this place, and I found it, and I took a picture, and I was all happy, and I don't think this is my picture, but I was, I found it and whatever. I drove past the most amazing rainbow, like full rainbow you've ever seen. It was like absolutely what you'd think of going to like New Zealand, right? You go, oh my God, this giant, perfect rainbow. But anyway, I got there, took a picture, and then went home, right? But here's what this, well, what else are you going to do? I mean, look at this. It's like a little field, right? I mean, here's what it means. This is what this sign says. This is what it means. The summit where Tamatea, the man with the big knees, the climber of mountains, the land swallower who traveled about, played his nose flute to his loved one. And there is so much wrong with that, right? I mean, right? I don't even know what it means to have big knees. I mean, I'm not quite sure what that means. And then the nose flute, I don't even want to go there, right? But anyway, that's what that means if you translate it from the original, like whatever. But anyway, if we wanted to put this in our hash table, we're in a little bit of trouble. Okay? If we want to put supercalifragilisticexpialidocious into our hash table, we're going to need a bucket, an array that has 26 to the 34 values in it, right? Do you know how big that number is? Right? If we go to, what was it? BC, right? And we did 26 raised to the 34 power. That number is not a number that you can fit in an array, as you cannot have that many values in an array in the current computers that we own. In fact, we'll probably never, right? That's just too big, right? So we got to think of something else. Okay, we have to think of something else to do here. In fact, for our dictionary, we certainly don't want like quadrillions of values in here, because our dictionary's only got like 700,000 words in it, right? And that's like including all those weird words like the chemical names and all that kind of stuff, right? There's just not that many words that we're going to need to store. So really, we're only going to want to have a dictionary like to store maybe 780, 800,000 words, right? Maybe a few for extra ones that come up. Yeah?
Can you nest buckets?
Can you nest buckets? That is a very good question. Hold on that question, because you're getting to what we're going to actually do. Can you nest buckets? Kind of, and you'll see what I mean. Okay, but very good point. By the way, this doesn't even count uppercase. Okay, and it's just too big for this sort of thing. Yeah. Well.
Since the English language only has 700,000 words,
Mm-hmm.
you could have created an array of like that huge size.
Yeah.
Like 99.9% of it would be filled with dead squirrels.
Absolutely, 99% of it would be, not more than that. You're right.
So,
Yep.
so couldn't you just, if there was a way to like compute a formula to convert that number to the index in the 700,000 array, could you work through it that way?
Yes. So you're actually getting to exactly what hashing is all about, what you're trying to do. What we're trying to do is compress this, right? So what Yuval says is, hey, there's going to be empty space for everywhere you can see. Like letters are not going to know, or words would not even know what neighbors are, right? I mean, it'd be like the Great Plains, right? Because there would be no, right? There's like no neighbors anywhere nearby. In fact, remember, this 26 to the 34th, for this many words, this is including every word that has like X, Y, X, Y, X, Y, L, Y, 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 Z, Z, you know, everything. They aren't even words. So yeah, so absolutely this is going to be, that would be way too sparse, is what we call it. So we're going to try to compress it. And that's exactly what we're going to end up doing. Okay, and that's really the big deal here. Okay, we want to conserve space. Okay, and we want to do this compression thing. But we also want to be able to store arbitrary words. We want to be able to store supercalifragilisticexpialidocious. We want to be able to store ox. We want to be able to store all the other words that are actually words. But we want to do it in a small enough space. The hashing function we used before isn't quite going to cut it. Okay? Not quite going to cut it. So here's what we're going to do. And in fact, that compression you're talking about is exactly this. Remember how we did this for a couple of other data structures, right? We took the modulus of the number, the remainder, right? The clock arithmetic is really what we're going to do, right? If you wanted to convert 13 to the clock, right? What is 1300 that we talked about for our calendar? What time is that in clock time? 1 p.m. Why? Because you did 13 modulus, or percent, 12, right? And that's how you ended up with the answer +1 as it turned. Well, no, actually not +1, just exactly that, right? So you do the hash code modulus the number of buckets. OK, so now we've arrived, right? We can now compress this. What's the problem with that? And it gets to what Dylan was asking a few minutes ago. Yeah? There will be multiple things in a single bucket, right? It's just like when I hashed all you guys, right? You all ended up like in the same, because our hash function for the decade of your birth was all the same, you all ended up in the same bucket, right? And I didn't care that you were all in the same bucket. But the problem is, how could I have used that hash function to locate one of you, right? I'd go, OK, I'm trying to find where Susie is, and I know that her hash, her decade is 90 something, so I'm going to look in the 9 bucket, and then there's everybody, right? Like who I don't know which one Susie is, right? So that's the problem, right? That's like the absolute problem. So if we do this, we will compress the hash table is what we're going to call it. Okay, this table is actually an array, and it allows us to do this. If we do this compression, we're going to have some trade-off. Okay, turns out the trade-off is we can deal with the trade-off if we make a couple other modifications to this. Okay, so here's what we're going to we'll drop back a little bit here and take a look at this. The number of keys that you want to store, in other words, the dictionary amount, say 700,000. Okay, needs to go into some array space that is, in this case, uppercase n, which is a little bit bigger than n. Okay, you really don't, if you could, you would want to put all the words in their individual buckets. As it turns out, we're not going to be able to quite do that. Okay, but you do want to make the little n versus big N, which we'll get to in a second as far as a ratio is concerned, is kind of important. The number of buckets you have versus the number of things that you are going to store there. And you don't always know that number ahead of time. So you might want to be able to rehash into a bigger size arrangement. But we'll get to that. Okay? So a hash table has this huge set of keys. Okay? If we want to do all the words, there's like so many keys available to us, because words could be every possible combination. But there's only a smaller number of buckets. Okay? We do this hash code, which we talked about already. Okay? And here's what it looks like. So this is kind of what we just did with you guys, right? Let's say we're going to insert 7, 18, 41, and 34 into this hash table with 10 values. If you were to do it this way, by the way, you would actually want the hash table to be not 10 values, but prime number of values. As it turns out, if you have a prime number of values, if you're doing mod a prime number, it turns out because nothing is actually the prime numbers are not divisible by anything, you actually order the bits, you scramble them up very nicely. Okay, so it's distributed if you use a good prime number for your modulus there, as it turns out. Okay, but in this case, we're going to insert 7, 18, 41, 34. Normally, we would have some associated definition or whatever value for this. I'm going to say the key is the value, kind of like what we've done before. All right, so we put these into the the table. It's exactly, this is our hash function in this case is the number modulus 10. So 7 goes in 7, 18 goes in 8, because it's now modded into there, just like the birthdays, right? 41 goes into 1, 34 goes into 4, and then we already know how to find them. If we wanted to look for where 7 is again, we hash 7. It turns out it's bucket 7. If we hash 18, it turns out it's bucket 8. And then we go to that location and find it. Easy to do. And now we've got them in here. There is none of this worry about overstepping our size of our array. But then we go and add 54. And that's where the problem is. Right? And that's where the problem is because we've now got this issue of 2 hashes going in the same one. OK? Any ideas what we call that? I already mentioned. I don't think I mentioned it. When 2 things bang into each other?
Hash class.
Oh, close. A hash class. I like that. Clashing. Yeah, I like that. It's actually collision. It's called a hash collision when that happens. And that will happen in your hash tables, and you have to be able to deal with it. OK? A collision is when several keys are hashed to the same bucket, OK? If the hash codes end up the same. And so we have to be able to deal with that, right? Let's go back here and just put these in here and think about how we might deal with that. If we hash both 34 and 54, Dylan earlier said, hey, can we nest these buckets somehow? I'm not sure nest is quite the right word. But in this case, what could we do to have both 34 and 54 in there? What could we do, Phoebe? Oh, you could also have a bucket for the tens digit too? That's an interesting idea. That would be the same problem we really had before, though, right? What if we had 300? Then you'd need a third set of, but I like the idea. But you're getting there, but what else could we do? Okay.
Make a 2D array, and then you only refer to one of the indexes.
Could you make a 2D array and then only, I'd have to think about that. I'm not, I think I get where you're going, but I don't think that's going to, it's not going to solve our problem if we have 3 or more digits, right? It's kind of the same idea. Yeah, Jason? There we go. Implement some sort of list. What if we had 10 numbers that hashed here? Couldn't we just have a list of 10 numbers here in a linked list form? You go to the hash, and then you start walking through the list. Question?
Well, I guess you'd have to walk through and ask about them.
You would have to walk through and ask. In fact, it's even harder than that. Well, it's not harder than that, but it's a little more subtle than that. Let's say there was definitions of ox and at. And let's say we used a hash code, and they both went into the same one. And you had a bovine animal used for farming, and when you are somewhere, or whatever, right? The definitions, right? So if you had ox, and it pointed to this one, all you've got are 2 definitions. How do you know which definition it is? How do you? How would you know what definition it is? Somebody knows the answer. How about, well, what could you do, Ethan? Store the keys and values, right? So you don't just store the value. You also store the associated key as well. And then you check and see, is the key what I'm looking for, the one I'm looking for, right? Yeah, Susie. Oh, it would mess with your O1 complexity. To a first approximation, it absolutely would mess with your O1 complexity, especially if you had a bad hash function. If we used a hash function of the decade of your birth, you all end up in the same one. I have to search through everywhere. Are you Susie? Are you Susie? Are you? You know what I mean? So I don't. And that does that degrades, right? It completely degrades. Yes. So hopefully we can come up with a better hash function that will avoid that. Nalani, did you have a question? Could you use a try? I'd have to think about it. I think a try is going to be prefix based, so it would be tough to do. Well, I suppose you could. Yeah, I suppose you could. You still got an order of the length of the word that you have to deal with. But yeah, that might work for this sort of thing. You wouldn't be hashing it in that case. You probably wouldn't bother hashing it in that case. But yeah, interesting idea. You could probably do that. So we're coming to a problem where we have that we would have to do some sort of linked list. Okay? All right. Here's what we do when we do that linked list thing. Okay? Oh, by the way, before I even get into that, one of the problems with storing your key with your value comes about when you don't actually want people to know what your key is. For instance, you guys have a password, right, for the computer systems here, right? When anybody ever lose their password and have to go and get it, yeah, you lose your password. You can go online and reset it or whatever. But do you ever lose your password and then they email it to you? Well, if they do, they probably shouldn't. Let me put it that way. Like there are places that I have gotten email passwords, and that's like bad for lots and lots of reasons. But the way it should be done, and the way it's done in the computer science department here is, you type your password in, it gets hashed, just like what we're talking about here. And here's one thing I haven't mentioned yet. Hashes are actually one-way functions. Okay? In other words, you can't go backward. A good hash will not be able to go backwards. Okay? The first one where we had ox and we had at and whatever in yes, they could go backwards because you knew exactly what bucket was associated with which word. But if a hash like this, once you do the modulus on there, right, it's impossible to tell 34 from 54, like given which one you were given, unless you have the key to look for, right? So when you're doing password hashing, which is what you do to actually make your password secure, you actually want it to be a one-way function, and you don't want it to be able to be stored with it. So yes, you can store the keys with the values, but this is probably not the best way to do it if you're doing something where you want it to be secure. You want to lose the key so that only the person who has to know it knows it. That's, by the way, how do they know you logged in? Or how do they know you're you when you try to log in? What do you think they do? They ask for your username, but then what do they do with the password? They're not supposed to know what it is. In fact, what sometimes it does is your browser will actually encrypt it, and then they'll never know what it is. What do?
They'll just check if something's there after applying the hash function that they applied the first time.
Yeah, they'll check the hash. They'll check the actual hash there, right? Which is one issue with, well, it's not quite the same idea, but different passwords can hash to the same value. So your password might be completely different than somebody else's password, but you could log in with your password to their account, but you'd have no idea who that is. And the good cryptographic hash functions, which is what we're talking about, actually make it very, very unlikely that will happen. Yeah?
Is that related to why in the computer department you can actually like get 1 or 2 characters wrong in your password and it's still like
Why can you get 1 or 2 characters wrong? No, that's just a bad implementation of what it is. What really? Well, there really is. I mean, what I think what's going on there is I think they've only allow you 8 characters, so anything after 8 just gets truncated. I think that's what it is. So yeah, it should not be the case that you could do that. And by the way, so for instance, okay, let's say that Sam has the password happy, right? Okay, and Phoebe has the password happy, but with an I, because she thinks she's being clever, because nobody will guess that, right? Right? Okay, right? So let's say that's the case. Well, that would be kind of clever, right? You know, you mix words, right? Well, if someone knows the hash for Sam's password, okay, it shouldn't be anything like the hash for Phoebe's password. They should be completely different hashes. In fact, 1 letter different or 1 character difference should make a completely different hash. And most of the time it does. Okay, if you do the hash function right anyway, most of the time it does. But that's another reason that you want the hash function to do that. Well, Dylan and then Susie. Yeah.
So how do they know that our new passwords, when our passwords expire, they ask us to make a new one, and then if you write one that's remarkably close to what you had before, they say, ooh, this isn't going to work.
How do they know that?
Yeah.
Good question. Anybody know?
I'm guessing that it has to do with
Well, what is the first thing you do when you have to change your password? Right where your old one is. And then they just have the hash, and then they check the hash against that. Now, the question is, actually, you know what? You brought up a very good point. How do they know it's like 1 or 2 characters off?
because if they
They're actually reading the old one.
Yeah. Oh, when they read the old one, they probably store it immediately. Yeah, that's probably what they do. Temporarily, yeah. They probably store the old one because they know, hey, you're changing it now anyway. We can know it. I mean, that sort of thing.
The new one,
Yeah.
and they have to read that.
They do have to read that, yeah. I mean, look, there is a bit of a breakdown there in that, but I mean, it's that part of it is not. That part of it is, I mean, you have to trust at some point there's going to be some layer of security there between your browser and the server, right? But what it does mean is that the people in the CS tech support, they can't go and look up your password, right? Now they can still see all your files. That's a different story altogether. But they can't look at your password. Like they can't say, oh, Margaret used this password here. Maybe she used it on Gmail, and go look at all your Gmail, because they have no idea. They only have the hash, and there's no way to go. There's no way to go backwards on that. Okay, Susie, you had a comment or a question. Okay, anything else on that before we go on? Okay, so we can do this thing called chaining. Now the next slide here looks a little crazy, but here's all it is. It's just a bunch of linked lists. You've got your table here, which points to this array, which is our hash table, right? This is like a pointer to the hash table. In here, x's mean there's no words hashed there. The arrows mean there are. And this is just a linked list. So if novel and supercalifragilisticexpialidocious both hash to the same value, then you could do this. You'd have a linked list here, novel and book, you store both, and then da-da-da-da-da, right? Same thing for these other ones, right? Same thing for like hint and word invented by, did you guys know that Shakespeare invented like lots and lots of words?
Yeah.
He totally invented lots of words. He invented the word hint. He invented the word excellent, I think. Bubble. There, what is it? Eyeball? Eyeball. Who thought? Shakespeare the biologist. I don't know. Right? So anyway, but that's all it is. Just a linked list. Just a linked list of values as you go along. And as Susie rightly pointed out earlier, this is not going to be great for our order 1 if we choose poorly. It's going to degrade. Yes?
So in this case, we're storing the key and the value.
In this case, we are. Yeah, in this case, we are. Most of the time, you can. I mean, most of the time, you can. And in fact, many languages allow you to do that too. So you can say, I have what we call a dictionary or a map or whatever this ends up we call this. And it says, give me all the keys. And then it will give you all the keys for it too. So you can get a list of all the keys. I mean, there's some other functions you can get out of it. Yeah, yeah, Jason.
So why linked list? Is that just
Why a linked list? I mean, you could do some other array, maybe a dynamic array if you wanted. I mean, it doesn't really matter. Either way, you're going to have some list, some container that's a list that has all the values in it. Yeah, no other real way to do that. Well, there are other ways to do that, not with chaining. But we'll get to that on Monday. Okay? All right. So we already talked about all this. Insert, find, and remove. We now know how to do all those. If you basically are always computing the hash code and then searching for it and then doing something with it, either inserting or retrieving or deleting. Okay? All right. What if we try to add 2 entries that have the same key? Like before, it was like the 2 keys hash the same value. We know how to deal with that. But what if they have the same key? Then we have to make a little bit of a decision, right? There's a couple different approaches. One approach is just replace the old key, the old value, with the new value because, well, too bad, right? That's the way it works. And in fact, Python, the language Python, does that. If you have something, a value key combination in a dictionary, and then you assign a new value to that same key, it will just get rid of the old key and put the new in there. That's one of the trade-offs. Or you could, whoops, I don't have what you can do the second thing. There's another idea too. The other idea is to say either randomly return one or the other, or return both, or make some other comparison to do it. But either way, you can store multiple values in there with the same key if you design it right. Most of the time, we don't do that. But if you design it right, you have to make some trade-offs. Okay? All right. So yeah, no other approach for some reason. You have to be a little careful here, though. Okay? You have to be a little bit careful, right? You can't go and change your object and expect to be able to find it again. Okay? If you change something about the object itself, so let's say that instead of hashing you guys by your birthdays, I went and hashed you by your middle names or something like that, right? And then some of you ended up getting married and changing your name and changing your middle name, right? Or something like that, because that happens fairly frequently. People change names all the time, right? And if you change your name, but the hash was based on your name, well, now you're done. Because you can't search, because the different name will have a completely different hash and you can't go find it. So you have to be really careful with that. If you're hashing objects and they're based on some property of the object, just make sure that you don't change the property in one of those properties, otherwise you'll end up with a bad hash. Okay? You've got to be very careful with that. Careful with that. Okay. All right. So we mentioned this before. The number of keys is going to be this lowercase n. The number of buckets available is going to be this uppercase n. If you divide the two, you get what's called a load factor. Okay? And the load factor is important because it tells you basically how bad you're going to do in terms of your complexity, your time complexity, right? If it was true that the number of keys were stored and the number of buckets were roughly the same, you're going to probably do OK, because there's going to be a bucket at least available. You have to make sure a couple of things. You have to make the load factor relatively low being 1 or less, right? or you have to make the hash code good for some definition of good. Okay, and I'll show you in a second some poor hash functions. And you also don't have duplicate keys because that actually changes the process again. Then you're going to get this order 1 behavior, as long as you meet these requirements. Yeah. Well.
If you have a low load factor,
Mm-hmm.
does that mean you'd have more buckets than words?
If you have, yeah, you might have more buckets than words actually. Yeah. And in fact, you do want slightly. If your perfect hash table generally has slightly more buckets than words, which is fine. Generally, I mean, if you're somehow trying to store like billions and billions and billions, yes, then you'll run into memory issues. But then you probably can't really use a hash table to begin with, right? Well, either way, not much way to use any kind of structure if you need to store that much. Yeah, Jason. I mean close to 1. Yeah, low being close to 1 in terms of the number. You want the number of buckets to be a little bit bigger, in general, than the number of words you're trying to store it in. Then we can come up with good hash functions that nicely distribute the words throughout those buckets. And you won't have too many collisions in there. Okay? If, however, the load factor gets big, then we're going to start degrading to this either theta n or big O n problem. Okay? If you all of a sudden got too big of a load factor. What do you do then? Lots of options. Well, few options. One of the options is make your buckets big, make more buckets, right? Do it just like a dynamic array, in fact, exactly a dynamic array. Just double the size of your dynamic array and rehash everybody. You definitely have to rehash everybody, okay, because you have a new hash function with a different modulus. Okay, but you have to do that. It takes time. In fact, it takes a fair amount of time because not only are you like copying elements, but you're copying and you're copying and you're rehashing, which is going to take some time. Yes.
So when you rehash, if you don't have the original key, do you just have to perform like a new hash function on the value that it's hashing?
Yeah, if you don't have the original key, you're in trouble. because think about it. I mean, you're going to want to search through it by the original key, right? I mean, so you're in trouble if you don't have those original keys. Yeah. Like for a password function, you're not going to do it. Now, passwords are normally hashes, but not normally hash tables. So slightly different idea. Passwords are normally like your password is next to your name in the whatever table they have of your thing, right? So your name is there, and then the hash is there as well. Now you could have a hash of a hash, right? You could have a hash table pointing to a hash if you wanted, but either way, you're probably going to have the original key in most cases for an actual hash table. But yeah. Okay, other questions on this? Okay. Remember, hash codes must be deterministic. They should be fast and distributed. Okay. The ideal hash, okay, maps to a random bucket. That would be a perfect hash, right? Map me to a random bucket somewhere. Okay. Is an ideal hash collision free? By chance you can get the same bucket. Okay. So let's see how your intuition works on this one. What does your intuition say? If we have 2,500 keys and we decide, you know what, I've got a really, really good hash function here. In fact, it's perfectly random. And I'm going to have 1,000,000 buckets. I don't even want to implement that stupid like collision business, right? Is this a good idea? What does your intuition say about 2,500 keys into 1,000,000 buckets? How many times are you going to collide in that, roughly? Any ideas? I mean, 2,500 keys, 1,000,000 buckets. What do you think, Jason?
More than you think, because if they're all evenly distributed, they would not be random.
If they were evenly distributed, they would not be random. I don't know. I mean, they're going to be random. So I mean, let's go through the process here, right? Pick a number, randomly throw it in the bucket of 1,000,000. Pick another number, randomly throw it in the bucket of 1,000,000. Do that 2,500 times. What's the odds that you get into a bucket that's already filled? Pretty low. What do you think? How many percent? 0.00. Okay. Other ideas? Yeah. Oh, isn't it like the birthday problem? It is exactly like the birthday problem. Anybody, you guys know what the birthday problem is in, not the birthday bucket problem, right? The birthday problem in math class? Well, hold on a sec. We're gonna let John explain that in a second. Let me show you what I have here. I actually wrote a little program that what it does is it does this. It actually tests this empirically. It actually says, give me a bucket of a million character array and take random 2,500 random numbers and throw them, or 2,500 numbers and randomly throw them in that bucket and see how often we get a collision. Okay, here it goes. 2,500, da 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 da. 98% of the time it did that. It actually does this 100 times and then tells me how many times that happens. 97%, 94%, 97% of the time. A collision 97% of the time over those 2,500 buckets, right? 97% of the time you throw numbers in there and you end up dropping one in a bucket that's already filled. John, you want to explain what the birthday problem is?
It's when you have a bunch of people in the room, like the more people there are, there's a really increasing chance that people have the same birthday.
There you go. There's an increasing chance that people have the same birthday when you have a certain number of people in the room. Do you know what the number is for about 50% chance? You remember what that was? 23, yeah, it was actually 23. So in this room right here, we have what, 50 people or so, right? There's almost like 90-something% chance that the two of you share a birthday.
We found 3 of them.
Right? You've already found 3 of you? Yeah, there you go. So it's a huge percentage. And this is exactly the same problem, right? This is exactly the same problem. So what that actually means, right? What that means is, and this is straight from Wikipedia here, if 2,500 keys are hashed, even the perfectly random choice, it's according to the birthday problem, a 95% chance, right? And what that means is you're going to have to deal with collisions, no matter what your hash table is, unless, and this is going to happen. We're going to talk about this on Monday, but unless you happen to know all of the keys in advance. If you know all of the keys in advance, then you can do a perfect hash function. Because then you know that you're not going to have two, you're going to be able to build your hash function, and it's actually pretty simple. You just basically order all the keys, right? And then throw them in the bucket based on that ordering. And then you can have a perfect hash function, right? But otherwise, if you don't know the keys in advance, you are going to have some collisions. So you have to be able to deal with it. Okay? And yeah, and intuition's a tough one on this one. Birthday problem is a tricky one to do intuition. Yeah. Good. Okay. So the compression function, in other words, the part that does the actual modding to flip or to randomly put the numbers in there, you can get some pretty bad compression functions in here, right? If you had a compression function that was just the number, or sorry, the hash code which was just the number, and all of those numbers happen to be divisible by 4, right? If you did mod of the number of buckets that was 10,000 buckets, well, guess what? 3/4 of the buckets wouldn't even be used. That'd be a terrible hash function, right? Because you'd end up dividing by 4, and then 3/4 of the time they'd never even land in that bucket, right? We talked about this a little earlier. Try to make the number of buckets prime, or if not the number of buckets, at least the modulus that you're doing somehow to get into those buckets. Okay, so if you do mod n, having n number of buckets be a prime number will make it nice and evenly distributed. Okay, here's a pretty good hash function for strings. If you are going to write a hash function of your own, right, and you're going to write a hash table or whatever of your own, this is a pretty good one to use. Pick a few numbers here. One of them should be prime, right, and 2 of them can be kind of any other numbers. The choice is more or less up to you. Try not to pick ones that are, well, I mean, picking them, I guess there's probably a better way to pick them than otherwise, but it doesn't matter as much as the fact that this one's prime. Multiply A times whatever hash code you came up with before you do all this modding. Add B, and then mod this, scramble the bits, and then mod by the number of buckets, and you're pretty good. Okay? This actually is a little bit slower because you're doing a couple different moduluses, and that's not that fast, but still relatively fast. As long as the prime number is much, much greater than the number of buckets, you're going to be OK. Okay? For instance, here we go. If you are trying to hash those ASCII characters, like the lab the other day, 1 through 120, or 0 through 127, the hash value here is going to be 127 times the hash. Well, I didn't actually figure the hash value out here. I think I goofed on that one. But the point is, you're going to have some hash value. You're going to multiply by 127, add the actual location of the I did do it here. Yeah, you're going to create the hash value by adding up these pieces of the string. That works. And then mod it by this giant, well, giant is a relative term, but this rather large prime number. Okay? And then return the hash value. That's not a bad hash function for a string. Okay? Uses a large prime. Uses each character in the string. That's probably good. Not the best, because it takes some time to go through each member of the string. But overall, it's not too bad. Bad hash codes. A lot of people say, hey, here's a good hash code. Just add up all the ASCII values of the word. Not so good. Right? Why is that not good? Well, first of all, most words never get above 500. That means you can only have 500 buckets. Not good if you're doing lots of words. Anagrams always collide, right? Because they're going to just adding up the individual letters. And you do have to go through the whole string again, so it's not good. What if you chose the first 3 letters, like we did before with the 2 letters, and just said only 3 and do it that way? Again, words generally have lots of prefixes, so you want to avoid that if you can. What if we changed p to be 127? Well, if we did that in the previous one, it is prime as well, but it's also this value. It turns out that's always going to be 0. Everybody's going to go in the same bucket. Don't do that. Okay? Not so great there. All right. So we're pretty much done with this one for this week. Next week, we're going to talk about, well, first of all, the lab is going to be on hashing. Okay? Second of all, we're going to do a little bit more analysis on the load factor itself. Then we're going to talk about better collision strategies, or rather different collision strategies, okay, that don't involve lists. Well, don't involve linked lists anyway. We're going to talk about, we already kind of mentioned perfect hash functions. Should hash functions ever be slow? That's an interesting question, because we've talked in our class so far, we've talked all about everything needs to be fast, 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 right? Well, sometimes we actually want hash functions to be slow. Think about why that's the case. And well, we might talk about we're going to talk about kind of where we use hash functions, what kinds of operations besides dictionaries we might use them. Okay? There are some, anybody ever heard of lolcat language? It's a language based on lolcats speak, like I has cheeseburger or whatever, right? There's an actual programming language that somebody's designed. And I wrote a little dictionary in there, so yeah. Yeah. It's anyway, and K thanks and K thanks bye, yeah. Yeah. Okay, so there's some references on there. The Wikipedia articles are pretty good. There's some good videos. Nice short one in Math World. Any other questions? Okay, I will see you guys Monday.